Here's a beautiful FRQ that covers stoichiometry, it covers solutions. It will also talk about how to answer these on an FRQ when you're taking the exam. Okay, let's get started. A 0.15 gram sample of solid lead-2 nitrate, pure substance, is added to 125 mLs of a 0.1 molar sodium iodide solution. So we've got a solid that we're dumping into a solution. They give us the mass and formula of the solid and also the volume and concentration. So we're going to be able to find those moles pretty easily. Assume there's no change in the volume of solution. As the lead dissolves, the chemical reaction takes place, and it's represented by the following equation. Okay, I give you the full molecular equation, lead 2 nitrate, or they probably just call it lead nitrate because almost all the time it's just lead with a +2 charge. They put in this 2 here to sort of help you along. And sodium nitrate. They dump the two together and you get this beautiful yellow precipitate. Here it is. Let me just show you a clip of some lead nitrate going into some sodium iodide solution. The precipitate, yellow, here it is made, and then we have some sodium nitrate left behind in solution. Let's see. A, calculate the number of millimoles of each reactant. All right. Let's start with the first reactant, which is our lead nitrate. We've got a mass, we've got a formula, and look, they even give us the molar mass of the lead nitrate. How nice. That's done pretty often on a question, so look for it because it may be hiding in there. So here's the calculation. We take the grams and divide it by the moles to get the molar mass. Now I advise very, very strongly to write this out. Now you may be so good, to know that, hey, all I got to do is grab my calculator and take this 0.15 and divide by the molar mass, 331.2, and get the answer. Now I'm going to do something very quickly. I'm going to change this to millimoles by multiplying by 1,000. It's such a small number that dealing with the exponential entries and all the rest, it's very often when you get small molar amounts, multiply by 1,000 and then use millimoles as your answer. 0.453. That's a lot easier to write than is 4.5 times 10 to the negative 4. So let me put away the calculator. And here's the setup. Now, as I said, you might be able to do this very quickly on your calculator, but you have to show your work. Whatever you type in your calculator, you've got to show in the FRQ. Now, I advise very, very strongly to use the units. And you probably are so good at this, you know how to do it automatically. But remember, on a test, there's a lot of pressure. And you're moving quickly, you're worried about the points, and it's really, really easy to flip a couple of numbers around. So say 0.15, I mean, you don't have to put in 0.150, but say 0.15 grams of lead nitrate, because when you see that on a piece of paper, you can identify it. In case you have to go back and do other parts of the problem, having it just 0.15 divided by 331 floating out here means nothing. You're using this not only to show your work, but to help you. It's worth the extra time. You might not have to do this entire ratio, but I would show 0.15 grams of lead nitrate divided by 331.2 grams and put the answer down. And that's another thing. Once you've got the answer, make sure you identify it. I'm going to put together an ICE chart because that always helps me. So here's the 0.453 millimoles. And I've got this as my reference in case, hey, something's wrong, I can go back to check my work. Now they wanted the millimoles of each reactant. So the other reactant is the sodium iodide. And this is a solution where you have 125 mLs and you have a concentration. Solutions and concentration, concentration times volume gives you moles. And they wanted to see if you knew how to do that. That was the other part of this problem. And here you can see I've got it. And on a calculator, you just simply do the 125 times 0.1. And there we go, 12.5 millimoles. Now, I multiplied the milliliters times moles per liter. Let me just grab a little pen here. And, the liters will cancel out. And you're left with millimoles. That's exactly what we want. And that's nice because we can put that 12.5 millimoles right here underneath the sodium iodide. Now we've identified it. And again, if I have to go back in terms of saying something's wrong, this will help me. And you want to help yourself as much as you want to prove that you've done this work. And again, if you don't show the multiplication, you're not going to get credit for an answer, even if it's the right answer. The readers have very strict instructions that if work is not shown, no credit, even if the answer is right. Now, you don't have to put the milliliters and moles and so forth. You just have to show that you've done some work. The primary objective of showing your work is to prove that you didn't copy somebody else's paper. But I advise very strongly to, again, use units. Don't have numbers without units because they're going to be mysterious numbers. A minute later, what was this 125 for? Well, you know what it was for because you identified it here. Make things easy on yourself. Okay, now let's go. Identify the limiting reactant. Well, that's why I like doing a ice table because it shows me what I've got for each substance. I have 0.453 millimoles of lead nitrate. And I would need twice as much of that of sodium iodide. I'd need 0.906, but I have 1205, so I have way more sodium iodide than I need. The limiting reactant is the lead nitrate. Now, make sure on any FRQ that you identify the limiting. They asked a question, you have to answer that question directly. So I wrote this sentence out. The lead nitrate is the limiting reactant. Step one, answer the question. Now, sometimes they'll give you 1 point for answering the question and 1 point for the support or the justification or explanation. So, readers constantly say that they feel so bad sometimes grading papers because they see a student has done the calculations but did not directly answer the question, and they can't give you a point if you don't directly answer the question. So think about that. Every time did I answer this question? Here it is. Yes, lead nitrate is the limiting reactant, period. Since it only requires 0.9 millimoles of sodium iodide to react, and pretty obviously we have this 12.5, which is more than you need. You don't have to write complete sentences. Your spelling can be atrocious. They want to see if you understand what a limiting reactant is, and this is enough to do that. Now, as I said, I really like ice tables. They're worth the time. And on this limiting reactant problem, you're going to end up having the 0.453 millimoles of the lead completely react, and there won't be any left. And the sodium iodide, let me grab that and pull it away. Don't forget, in terms of stoichiometry, you'll need twice as much sodium iodide, but you have 12.5, so you're going to have left over 11.6 millimoles of sodium iodide floating around in this solution. Now, they didn't ask for it, but you could identify, in fact, this should be a plus, not a minus. In fact, let me just change plus sign there. And in the end, I'm going to have, again, it's going to be one lead iodide, 0.453 millimoles of lead iodide. And you can figure out its mass by multiplying by the molar mass, which is pretty big. I looked it up already, 461, but they didn't ask for that. Now let's go a little bit further here. This is C. This extra stuff, I just wanted to end up showing you the stoichiometry, a little bit of teaching stuff. Write the net ionic reaction for this reaction. Okay, now we're making one solid. This is what's made the lead iodide. Now, they may not have given you the lead iodide equation, but you could figure it out. The lead has a +2 charge. And with a net ionic reaction, you only worry about what's changed. And the only thing that's changed that you saw that was produced was the lead iodide. And you will say, okay, the lead plus 2 ions reacted with the iodide ion. So you need 2 of them to make the lead iodide. Plus 2 charge, 2 negative 1s, always making a neutral species, or making a neutral species here. Now, as this says, the lead nitrate is a spectator ion, and they don't do anything. They don't even applaud. The question is right here: what is the concentration of the nitrate ions? And that was calculate the molar concentration of the nitrate after the reaction is complete. So the nitrate didn't do anything. It's here before and it's here after. So therefore, this nitrate, which is present, 0.906 of it, there are 2 nitrates for every 1 lead. So the nitrate concentration is going to be twice that of the lead. And it has a volume, here we go, 125 mLs. And if you take this millimoles and divide it by the milliliters, I would just take those answers if I need to show my work. And I would just put a division sign here. And obviously, in this case, let me grab my pencil. The millis, the 10 to the negative 3, cancel out and I get moles per liter. Let me pull up the calculator and we can do that. We've got our 0.906 millimoles of nitrate floating around in 125 mLs of solution. We have both in millis. And there we go, 0.00725. Beautiful. Now for this last part, which is a called diagrams. And it says, which diagram below best represents the results after the mixture reacts completely as possible? Okay, let's see. We had a reaction and it made solid lead iodide. So this says solid lead nitrate, so forget that. That's going to be wrong because we have to have our A is gone. Solid lead iodide as our precipitate. Now in our reaction, we had leftover sodium iodide. All the lead was used up because it was the limiting reactant. So if we have a reaction with some lead floating around, there it is. No, the lead's the limiting reactant. We can get rid of that too. Now we had excess iodide. So we're going to expect to see iodide ions, and here they are. Here is the iodides, and here's their sodiums. And of course there are nitrates present because we had the nitrates as being spectator ions. So this experiment, this diagram is wrong because it doesn't have any iodide in it. And that gives us C as our choice, where we've got floating around sodium ions. We've got a total of 1, 2, 3, 4, 5 of them. And that's a charge of plus 5. And then we have 1, 2, 3, 4 iodide ions floating around, which is a negative 4. And this one nitrate making negative 5, it's neutral. It's a perfect picture. But we didn't have to do that counting because we know this was the only possibility. So that's it.